Right. My name is Archie Jarman, and I'll be your moderator for this webinar. We'll be covering 6 post-harvest technologies that were advanced or developed by the former Feed the Future Innovation Lab for Horticulture at UC Davis. I wanted to go through some quick logistical items for the webinar. All participants are muted, and please use the Zoom chat feature located at the bottom of your screen to ask any questions of the presenters. There's a dedicated Q&A session for each technology when you can ask these questions. Also, please take a moment right now to introduce yourselves in the chat, where you're from, your name, where you work. After a brief introduction, the webinar will follow a format of playing a short video about a specific technology, then a brief presentation from an expert on that technology, followed by a question and answer period where participants can ask questions for that presenter in the chat box. The videos are also posted on YouTube, and a link will be shared in the chat in case there are any technical difficulties with the quality. As I mentioned before, the session is being recorded, and a recording of the webinar will be posted on the Horticulture Innovation Lab website. But yeah, I want to just say thank you for joining. And now I'd like to turn it over to Dr. Beth Mitchum, former director of the Horticulture Innovation Lab and center director of the Post-Harvest Technology Center here at UC Davis.
Thank you, Archie, and welcome everybody. We're so glad that you joined us for this webinar. Hope you, and thank you to all the speakers who are joining us today. So I wanted to, as Archie mentioned, the Horticulture Innovation Lab was engaged with researchers to develop the technologies that you're going to hear about today. And this program ran for 10 years up until just about a year ago, and was involved with helping smallholder farmers in emerging economies around the world, especially in sub-Saharan Africa, Southeast Asia, and Central America, helping these smallholder farmers to be more effective and efficient at growing fruits and vegetables, and also marketing those fruits and vegetables to improve their livelihoods, but also to make nutritious foods more available in their communities. Within our program, we focused a fair amount on that connection between the farm and the market, and the post-harvest handling that is essential to realize the investment that is made in producing various crops. We feel like this linkage is quite poor in many parts of the world, and there hasn't been enough attention focused on allowing farmers or enabling farmers to effectively get their harvested crop to the market safely and in good condition. And it is essential for the success of those farmers, as well as to increase the amount of healthy food available in the community. If you look at a lot of these countries, you find that there's a few reasons why we see a lot of product loss after harvest. And loss could be just a degradation in quality, or it could be just complete waste. One is high temperatures that the product is exposed to after harvest. Another related is water loss, which leads to wilting, physical damage from rough handling, decay from various microorganisms degrading the product, and inadequate drying and dry storage. These are really the most important factors leading to loss. Water loss is a major issue, and it happens when the product is held at high temperatures or not protected from the sun. It's especially bad when the relative humidity is low. And if there's no packaging to keep the humidity high around the product, then water loss can be very, very high, as you can see in this photo. Another big challenge is the lack of cold chain in most of these countries. So cold chain is very limited and not generally used for fruits and vegetables. So this means that the temperatures after harvest can be very high, especially if there's sun exposure, and this leads to water loss, increased decay, and over-ripening. It also means that the farmer has less time to get that product to the consumer or to the final market. And this is true not only in emerging economies, but for small farms in the United States as well. If you can't store your product after harvest, then you have to sell it as quickly as possible. It reduces the farmer's ability to negotiate price and whatnot. It also reduces the availability of these nutritious foods during the times when they're not being produced, when the weather is not conducive to production. And so cold chain really is a challenge that needs to be addressed in order to make these perishable foods available for people's nutrition security. So handling of fruits and vegetables, the packaging is not sufficient to protect the product from physical damage, as you can see in these photos here. And the plastic packaging can help to reduce water loss, but these packages are not providing any protection from physical damage. And there's lots of data available, such as this data here from Thailand, collected many years ago, showing the amount of physical damage, 25%, even sometimes more of the product with physical damage, similar amount of product with diseases or disorders. So leading to a lot of loss. And then finally, we're going to touch on the importance of dry chain, making sure that products that are dried after harvest, whether they be fruits and vegetables, nuts, grains, or legumes, that those products get sufficiently dry and stay dry to reduce the potential for contamination with mold and toxins that are very harmful to human health and nutrition. So this webinar is going to talk about some of the technologies that have been developed, and we believe that effectively introducing appropriate technologies can address some of the challenges that I've just briefly laid out for you. And so, but that I think we want to emphasize effective introduction and also appropriate technologies. And those are some of the challenges that we have to consider as we work with these new technologies. So I'm going to turn it back to you, Archie, for the next presentation. And thank you again, everyone, for joining us today.
Thank you, Beth. That was great. That was a very nice introduction into the technologies that we're going to be presenting. And we'll start with playing a short video about the DryCard and then have a presentation and then a Q&A period about that technology.
Farmers and traders around the world produce crops that need to be dried and stored for consumption or sale. However, knowing whether the product is dry enough to be safe for storage then for consumption is a challenge. Storing improperly dried products can result in moldy food, food losses, and food that is unsafe to eat. Using the Horticulture Innovation Lab's one-page information sheet on how the dry chain works as a guide, this video will walk viewers through how to properly implement the dry chain and how to properly use the DryCard. The University of California Davis's DryCard is a simple, low-cost dryness indicator that farmers, traders, and researchers can use to verify whether their product is dry enough for storage and whether their product remains dry during storage. Using a cobalt chloride strip that reacts to equilibrium relative humidity, or ERH, in the air of a sealed container and a corresponding color chart, users can accurately identify the dryness level of their product. Anything below 65 ERH, or not pink, being dry, and anything above 65 ERH, pink, being wet. One DryCard can provide repeated readings of dryness for up to 2 years if stored properly. Below 65 ERH, molds, bacteria, and fungus do not grow, so as long as a product is below 65 ERH, it is safely dried for storage or has been safely stored. This is the case for any dried commodity. This video explains how to properly use the DryCard. During or after drying, take a sample of the dried product and place it in a sealed container with the DryCard. For even more accurate measurements, keep the sample in the sealed container for several hours, then take the measurement. The container can be anything that is airtight. Using an airtight container ensures that the DryCard indicator strip is reading the ERH in the air around the product, which is equal to the dryness or water activity of the product itself in the container. Make sure the sample includes product from different depths and areas of the batch to get a good representation of product dryness. The user can also take multiple samples, either multiple times or using multiple DryCards to get an even more accurate estimate of the overall dryness of the product. After the sample and the DryCard are both sealed in the container, wait 30 to 60 minutes to allow the product moisture to equalize with the air around it in the container and the cobalt chloride to react. The DryCard's cobalt chloride indicator strip will change color, indicating the dryness of the sample. After 30 to 60 minutes, remove the DryCard and match the color of the indicator strip to the color chart. The DryCard can be used with any dried commodity, including grains, peas, dried fruits, vegetables, fish, and meat, with the key indicator being not pink is dry, pink is wet. If you have a pink reading, the product needs to be dried more and tested again after drying. If you have a not pink reading, the product can then be safely stored. To check whether the stored commodity has remained safely dry, simply place the DryCard in the storage bag, seal the bag, and wait 30 to 60 minutes. Then remove the DryCard and compare the color of the indicator strip to the color chart for a reading. Placing the product in storage bags that do not allow for water to re-enter the product will help the product remain dry and not grow mold or fungus. This storage is called hermetic storage. To check the dryness in hermetic storage, simply place the DryCard in the bag, seal the bag, and wait 30 to 60 minutes. Then remove the DryCard and match the color of the indicator strip to the color chart. The process of drying products properly to below 65% ERH, then accurately checking the dryness of the dried product, then storing the product in watertight storage and confirming that safe dryness, as indicated by the green arrows on the right side, is called the dry chain. Make it dry, keep it dry. When you're done using the DryCard, store the card in an airtight container with some dry grain and out of the sunlight. This will keep the DryCard's indicator strip vibrant and clear for up to 2 years of repeated use. For more information about the DryCard and the dry chain, or where to buy a DryCard around the world, visit www.horticulture.ucdavis.edu.
So hopefully that video was helpful. I'm going to now turn it over to Dr. Jim Thompson, Emeritus Professor of Plant Sciences at UC Davis, who will be following that video with a brief presentation about the DryCard. Take it away, Jim.
To give you some background. First, Archie mentioned in the video, equilibrium relative humidity. It's a simple idea. It's the relative humidity above, in the airspace above a product stored in a sealed container. So it's the humidity that's in equilibrium with the dryness of the product itself. It's measured as regular relative humidity, percent relative humidity. Some of you may be familiar with an idea called water activity, and that's just a decimal version of equilibrium relative humidity. So a water activity of 0.65 equals an equilibrium relative humidity of 65%. Same idea. This concept of water activity and equilibrium relative humidity is well established. It's used extensively in the food industry and is starting to become more widely used even in agriculture. Agriculture tends to use moisture content, and you notice that we have not yet used that word so far. We use the word dryness. It's a more valuable measure of the stability of the product than moisture content. And I'll explain a little bit about that in just a minute. So this is some more detail about why equilibrium relative humidity is important. Now, this is a chart that shows the effect of, you can see on the right-hand axis, equilibrium relative humidity, and then temperature is on the bottom axis. So bacteria, fungi, and insects, their growth is influenced by equilibrium relative humidity, but also temperature. And you can see the first red line in the top there at 65% ERH, which equals about a 13% moisture content for maize. At that point, microbes stop growing, and this is all of them. Bacteria have stopped growing at much higher equilibrium relative humidities, but fungi, the fungi that grow at the lowest dryness levels stop growing and reproducing at that 65% level. That's the crucial level that we're interested in, and that's what we talked about in the video. Now, insects will continue to grow, and if the product is dried even further to about 35% ERH, then even insects will not grow. But usually that's too low a moisture content for commercial use. It takes a lot of energy to get down to that low moisture content. And we use hermetic storage techniques to control insects rather than equilibrium relative humidity. Now, what about this issue of moisture content? There is a relationship between moisture content and equilibrium relative humidity. And this shows you an example for cocoa beans. At the 65% equilibrium relative humidity, that critical number we're after, is just below 7% moisture content. Now, this number is different for various crops. So maize, it's at about 13.5%. It's very much influenced by the oil content of the product. And moisture content can be quite different. That is, the moisture content that corresponds to 65% equilibrium relative humidity can be quite different for different commodities. But a lot of people want to know, can we still use equilibrium relative humidity to measure moisture content or estimate it? And the answer is sort of. And the reason is all the relationship that we saw just in the previous slide is actually affected by the time after drying. Product straight out of a dryer has a dry surface, and its equilibrium humidity is lower than it's going to be after the product has equilibrated in moisture content. And that equilibration period can take 4 hours for rice. It may take 24 hours for larger diameter product like tree nuts. It's affected by temperature. That relationship is also affected by whether the product is gaining moisture or losing moisture. It's also affected by the cultivar, growing conditions, and even drying with high temperature air can influence that. And so with all these variables, it makes it difficult. If you, for example, have a crop that's handled in the same cultivar, handled the same way from grower to grower or season to season, then you may be able to get a prediction, a relationship between equilibrium relative humidity and moisture content. And this is what we've done before. So we would take a product that's at the critical moisture content for acceptance in the market, say 13.5% for maize, which is a typical number for moisture content. We'll get a sample or two at that critical moisture content. Put the dry card in the bag, let it equilibrate, in this case for 24 hours, because we want a very reliable reading, accurate reading. And then on the back of the dry card, we'll draw a rectangle where the color of the humidity strip matches the color of the dry card reading strip next to it, okay? And so that from then on out, you can use that color as an indicator of that threshold moisture content. And you know the threshold moisture content varies between buyers. Buyers' moisture meters vary in accuracy. So this allows an individual calibration for a particular crop measured with a particular moisture content meter. So let me end with that. And Archie, do we have any questions that we can talk about?
I can ask a question.
Yeah.
I'm curious how you've gone about, because I understand that moisture content is kind of, it's been an industry standard. Do you have any strategies for explaining to users, you know, or potential adopters of the dry card, why, you know, how they can make the transition between traders and farmers and using relative humidity versus moisture content?
Good question. And I think one of the key issues is to emphasize the value of equilibrium relative humidity. Many growers eat their own harvest, a portion of their own harvest, maybe a lot of it. They want their families to be safe. And this is a tool that can help them guarantee that the products that they grow are safe. Now, with that sort of encouragement, then the question is, since many of the growers don't have moisture meters, they're kind of at the mercy of the traders to know whether their product is adequately dried. And if it's not dried, they pay a price in the market, they get a discount, for example. So I think the thing to do is to work with individual traders, get them to become familiar with the dry card. And then for the grower and the trader to make this calibration like we talked about, so that the trader understands that a particular dry card reading is correlating with his moisture meter. That way the farmer and the trader know that they're talking about the exact same conditions. And when the trader uses the moisture meter, they can be confident that the dry card reading will equate to the reading, the threshold reading for the moisture meter itself. So the basic answer is experience, getting people to use dry card, become familiar with it, and become familiar with its value. Another question, Archie? Oh, I haven't heard Archie at this point. Do we? Okay.
Beth has a question about, can you talk more about why moisture content is not the same as equilibrium relative humidity and what factors cause the difference in readings?
The short answer is that list of things that I showed earlier. The cultivar, the way it's grown, the weather conditions when it's grown, the oil content, as I mentioned earlier, high temperature drying influences it, whether the product is losing moisture or gaining moisture. There's just all these variables, and I can't give you an explanation for why each of them has an effect, but they have been documented. So we do know those effects are there. So the relationship is loose, it's variable. And actually, the dry card and equilibrium relative humidity are, that threshold of 65%, as you mentioned in the video, is a standard that works for evaluating dryness of the product for anything. Moisture meters, on the other hand, are subject to errors in calibration errors in use, sampling errors and things like that, let alone cost. They're, at least 100 times more expensive than a DryCard. And so the only reason we use moisture meters is that products are oftentimes purchased by weight. And the purchasers want to know if they're buying too much water. And I understand that. But when traders and growers get used to the idea of using DryCard, they'll become more comfortable with using it as a good indicator of proper storage moisture and handling moisture.
Great. Thank you, Jim. That was great. Hopefully there'll be some more questions coming in the chat if you can keep an eye on that. But we'll move on to the next technology, which is the drying beads, and I'll play a quick video. And yeah, thanks so much again, Jim.
My pleasure.
Rhino researches drying beads are zeolite clay desiccant beads with an exceptional capacity to absorb water molecules. They are far more efficient than silica and can dry products to below 10% relative humidity. Additionally, the drying beads can be regenerated in a simple oven, allowing for repetitive use. As a demonstration, we have placed improperly dried chilies in 2 sealed jars, and as the DryCard indicates, they are too wet for storage. As you can see in this video, the chilies in both jars were not properly dried, and the DryCard is indicating that they are still too wet for storage by rapidly turning pink within the jars. However, we then placed drying beads in the jar on the right, and as you will see, the desiccants quickly absorb moisture in the sealed container. Now in this video, we placed drying beads in the jar on the right, and you can see by the DryCard that the drying beads are rapidly absorbing moisture within the container, turning the DryCard to blue. There are some disadvantages for small-scale producers and traders, primarily the cost of the beads, approximately $11 US per kilogram, but also the lack of access to an oven that can maintain consistent temperatures for several hours. To mitigate these disadvantages, the Horticulture Innovation Lab with Rhino Research worked with large-scale vegetable seed suppliers in Bangladesh to create a system where containers with the drying beads are distributed by the companies to small-scale seed producers who return the units with the seed in the desiccants back to the company. The companies themselves had the capacity to regenerate the beads in ovens that they had on their facilities.
Well, now after the presentation or that brief video about the drying beads, I'd like to turn it over to Dr. Kent Bradford, also emeritus professor at plant sciences at UC Davis, who will give us some more information about the drying beads. Take it away, Kent. Kent, I believe you're muted.
Okay, can you hear me now?
I can.
Can you see my screen?
I can.
Okay, great. So I'm Kent Bradford. I'm a professor, or emeritus professor, actually, at UC Davis. My specialty is more in seeds, which are also a commodity that we need to dry to maintain their viability, but also a lot of products, as you saw before, maize and so on, are grains and need to be stored dry as well. So you saw this image before in Jim's talk, just pointing out that drying is important to prevent both bacteria and fungi, particularly fungi that can produce aflatoxins and other products that are harmful, and also to prevent can also prevent insect invasion as well. The problem is, in some cases, it may be difficult to get products to those dry levels. And particularly, I've boxed here a certain area, a range of warm temperatures and high humidities that are common in the tropics and humid regions of the world, where just ambient storage in porous containers is not going to work, because they're continuously into conditions where these problems can occur. So as was described by Jim, there's a relationship between seed moisture content or commodity moisture content and relative humidity. Previously, we didn't have these very simple humidity meters. We used to have to measure humidity by swinging thermometers in the air and so on, and it was a bit awkward and certainly difficult to measure inside of closed containers. But now we have very inexpensive electronic meters, and particularly the DryCard is an excellent way to very cheaply and very accurately actually measure the equilibrium humidity, which is a substitute for moisture content, as Jim described. The drying beads are a technology we investigated with support from the Horticulture Innovation Lab, developed by a company called Rhino Research in Thailand, based upon a zeolite-based clay that absorbs moisture. So the beads are this clay material that's baked, so they're sort of more like a ceramic. And when you enclose those beads in a closed container, they will absorb the moisture out of the air. And when they do, then the commodity will evaporate moisture from it to the air, and then it just removes the moisture and it's trapped in the beads. The beads can then be heated and reused, as was mentioned before. It does take a relatively high temperature to reactivate the beads, and you do need an oven that can do that above about 200 degrees centigrade to reactivate the beads. Fortunately, they're fairly robust to that. That is, they can be used an indefinite number of times, as long as you don't break them or something. I'm going to spend most of the rest of my time just talking about a recent project, just as an example of how these could be used. This is a study we just recently published. It was done in collaboration with a group at CIMMYT, the International Maize Center in Mexico, under the direction of Denise Kostic, who was the germplasm manager, director of germplasm storage and preservation there, and Filippo Guzan, who was a postdoc there. This was actually conducted in cooperation with a program in Guatemala that was trying to develop community seed banks to enable small farmers to preserve their planting seed. Often they're storing their own seed from their maize, for example, and using it the next year. The problem is, under their conditions, continuous high temperature and humidity, often by the time the next planting season comes, their seed has lost half or more of its viability. So it's not a very good system. Generally, they're storing their seeds in their own houses in porous bags, and this results in the problem. So they were trying to establish community seed banks where growers could bring seeds in, sort of put them on deposit, if you will, store them properly, and then come and pick them up next year at planting time. So they did an experiment on this. They had compared to the storage in mesh bags, which were porous and subject to the ambient conditions. The seed banks were using hermetic flasks, so they're sealed, but they were not, their practice was not to really try to dry much below what they could obtain under ambient conditions or sun drying conditions. And that was to be compared with the condition where they put the seeds in with drying beads and as you can see here, DryCards, to dry them to a lower level. So these shows you how useful the DryCards are, where you can see the ambient conditions are pink, but what they were using in hermetic flasks, because they were just taking that sort of grain and putting it into these flasks, was also pink, but with the drying beads in with the grain, it was quite blue and dry. So just this is showing the germination viability of these seeds on the axis. A very similar result for seed damage that is due to insects and other fungi and other problems. But this is 3 different locations they tried. And what you can see is that those seeds that were stored with the drying beads, where they lowered their moisture content to 11.6%, maintained their quality, both germination and physical quality, over 6 months time period without any loss at all. Whereas under the other 2 conditions, both conditions, you can see pretty dramatic losses in viability and quality. So this is a case where obviously the open storage, that is the porous package storage, was not good. But in fact, in some cases, the seed bank storage was even worse. That is, without drying the seeds and then storing them in a hermetic condition, turned out to even be worse than not storing them in a sealed vessel at all. So the drying part is very critical to maintaining the quality. And as you see, the moisture content just under ambient conditions was more like 15 to 19%, way up in the range where it's going to be potentially damaging. So we've mentioned the dry chain. The dry chain is analogy to the cold chain or the cool chain that Beth Mitchell mentioned earlier for seeds, but also for any dried foods. It basically says harvest the material, which is generally not dry enough for long-term storage. Then dry it, whether by sun drying repeatedly, as is often done by some of the techniques you'll hear about later in this talk today, drying beads or some other desiccant, or heated air dryers, which are less efficient in hot, humid conditions, but better than having moist material. The key then, and particularly in humid conditions, is to package and store those those commodities or seeds in waterproof containers so that they're not able to reabsorb the moisture from the atmosphere. Maintain that during transport, because in some cases there are certain systems where bags are provided to farmers and they can store their material, but then they retain those bags and then they're dumped out again into the air to be transported and stored in bulk by traders and millers and others. So it's important that it is a chain. It's just like fresh produce that needs to be cooled all the way through, so do dry materials. And that way you can get to the other end with either viable seeds or safe food. Some things not to do is not to store moist bulk seeds and grains. So store them together, that's even worse. Porous packaging, it's not adequate in these places where the external humidity is high. If you're using porous packaging, it's best not to just leave them open. If you go through markets in a lot of that part of the world, you see plastic bags used, but they're not being used necessarily properly. That is, they're not really careful to protect the commodity from the ambient atmosphere. And as I mentioned, if those had been plastic bags that these workers had, it would have been better to leave them in them because they're now taking them to market. And once they're out, exposed again to the atmosphere in humid climates, they will absorb moisture again. So again, that's what we call the dry chain. And as Archie mentioned earlier in the video, it basically says to make the commodity dry and then keep it dry. So if it's not dry enough, you need to dry it. And once you have dried it, it needs to be stored in proper packaging to protect it. So that's pretty much it. Thank you.
Thank you, Kent. We do have a question in the chat. As Chom was curious if there's a difference in the ERH level that you're looking for grains dried for consumption versus for seeds, for preservation for seed.
Well, actually for seed, we can go lower. That is, that level that's mentioned at about 65, 60%, which is sort of the target for grains, 12% or so, 12, 13%. That is adequate for storage, and it's more optimal for milling. That is, if you dry the grains much lower, which is okay for the viability of seeds, it can create problems for the milling. That is, they don't mill properly. And say rice, for example, if it's too dry, then you get cracking in the grain, in the endosperm, and so on. So that's the main feature, is more about the physical maintenance, cracking, and so on. Most seeds that are dryable can go drier than that. As we mentioned, to fully protect them from insects and so on, below about 35% equilibrium humidity. Most international germplasm storage banks now are bringing their seeds to equilibrium with 15 to 20% humidity before packaging and storing in cold storage. So most seeds can go lower. There are exceptions to that. Coffee, for example, is a seed that you can over dry and so on. I think a lot of the concern about over drying of grains and so on has been because the normal way to do that is just to put them at high temperature and hot air for a long time. It takes a very long time to get them down to those lower levels, and then they're exposed to high temperatures, and which is aging them at the same time. That's why this desiccant approach with the drying beads is safer. That is, it doesn't use heat. the water does not evaporate rapidly and cause tensions, physical tensions within the seed. It's evaporating at the rate that it can be internally moved to the surface and evaporate. So it's a fairly safe way to go.
Great, thank you for that, Kent. We're a little short on time, so I'm going to move on to technology, but there is a question in the chat if you can answer that. And
okay, I'll do that.
And then we're going to move on to the chimney dryer. I'll play a short video about the chimney dryer.
Researchers at UC Davis designed a solar dryer for small-scale farming systems around the world. The Chimney solar dryer dries fruits and vegetables twice as fast as traditional solar dryers by combining a table where heat from the sun can collect with a chimney that creates continuous airflow around the product. The Chimney solar dryer is built with materials that are easily available in local markets around the world: wood, clear plastic, black plastic, mesh screen, and basic carpentry supplies. The dryer is built in 4 main parts: a drying table covered in black plastic or black fabric, a chimney covered with clear plastic, drying trays made with plastic mesh or metal screen, a plastic cover of clear polyethylene, Though the exact size of this design can be adjusted, for this video we are building a chimney dryer that is 4 meters long, 60 centimeters wide, and has a chimney that is 3 meters tall. We start by building a sturdy frame for the table, including slats across the top for additional support. Then stretch black material or black plastic over the top and sides of the frame, securing with staples. On top of the black material, attach 2 wood strips that will lift the trays off the table. Next, build a similar frame for the chimney. The chimney must be the same width as the table, in this case 60 centimeters wide. Cover the whole chimney with clear plastic except for the opening at the top. Now build trays that will hold the fruits and vegetables to dry. Cut mesh into squares 60 centimeters wide. Then attach 2 pieces of wood under the mesh opposite each other. Secure 2 more pieces of wood on top of the mesh on the 2 remaining sides. Secure mesh to wood with staples and screw wood corners together. Build 5 trays for this chimney solar dryer. Finally, put the pieces together. Join the chimney to the table by screwing 2 vertical boards. You may want to anchor the chimney to the ground with stakes. Place the 5 trays on the table, then build shelves at both ends of the table to hold a pole. Carefully cut an opening in the chimney plastic so the air will flow above the table and under the shelf and plastic cover. Drape the clear plastic cover over the table and shelf, pressing the clear plastic tightly against the chimney to prevent air from escaping. First, rinse with clean water. Small and thin items like leafy green vegetables and herbs may dry in a few hours, while larger, bulkier products like tomatoes or mangoes will take a few days to dry. You can also dry bulky products more quickly if you remove the pits, peel the product, or cut into thin pieces. Next, arrange the product onto mesh trays to dry. Trays that are loaded more sparsely will dry more quickly than trays with a lot of product on them. The fruits and vegetables will shrink when they dry, so you can overlap them slightly. When placing the trays, leave the first space open, farthest from the chimney. This helps the air warm before moving over the fruits and vegetables. You can stack the trays too high as long as the lower product doesn't touch the tray above. Make sure that the plastic cover doesn't touch the product and slow airflow. You will only want a few centimeters of headspace above the fruit and below the plastic covering to keep the air flowing. Secure the plastic cover and make sure that the airflow entrance and chimney exit are not blocked so the air can flow only in one direction. The temperatures and humidity in the dryer will vary, so rotate the trays about twice per day for more uniform drying. Air temperatures, humidity, and weather can affect drying time. The Chimney solar dryer works on sunny and cloudy days. However, it does not work during extended periods of rain or heavy clouds. First, selecting a site for the Chimney solar dryer. Before you build the dryer, you will need to find a flat outdoor area to use it. The area should allow the whole dryer to have good sun exposure. Clear away tall grasses and rocks that could damage the plastic. If you're in the northern hemisphere, you will want to orient the dryer so that the chimney is at the north. If you're in the southern hemisphere, then you will want your chimney to be at the south. Optimizing airflow. The clear plastic on your completed chimneyed solar dryer should be tucked tightly so that air can flow only in one direction, entering at the end of the table, flowing across the fruits and vegetables to dry them, and then continuing up and out the chimney. Make sure to tuck tightly behind the vertical boards that connect the table to the chimney, around the chimney window, on the ground on either side of the table, and under the chimney. But leave an opening into the soil for when it rains. How to know if the airflow is working? Sometimes the suction from the chimney will make the plastic over the table concave as the air is being sucked through the dryer. You can also test the airflow by attaching some small strips of tissue paper to the pole above the product in the middle of the table. When the air is flowing correctly, these strips will move with the air. For more details on this low-cost solar dryer, check out the UC Davis Chimney Solar Dryer Manual on the Horticulture Innovation Lab website.
I'd like to now introduce Rana Islam. He's a current graduate student in Dr. Beth Mitchum's lab, and he was a former project leader in Bangladesh working with the Chimney solar dryer. Rana, if you'd like to take over and present about the Chimney solar dryer, that'd be great.
Thank you, Archie. So I'm sharing my screen. I think it's visible now.
It is. We see you set us perfect.
Yeah. So I'll talk about solar chimney drying in Bangladesh. So in Bangladesh, we usually dry, these are our common drying products: chili, fish, pulses, cereals, mangoes, groundnuts, sometimes sunflowers. And if you look at the picture, these are the way we dry, and these are not very hygienic. They just lay the product on the ground in open air, and sometimes even use their feet to spread the product. So yeah, these are not a very hygienic practice, but they are very cheap, and you don't have to put you don't have to put much effort for doing this. But once we introduced chimney dryer in Bangladesh from our project, we got these are the perceived benefit that the beneficiaries felt. Like they say, it's easy to construct. If you see the videos, it's very easy. You can make the chimney dryer with locally available materials, and you don't need a very good carpentry skill for this. And it dry faster, because I think video explain it very pretty good how it increase the drying speed. And it also keeps the product safe because it's protected, so a chance is lower that a dirt and other things will get into the food, the product from outside. And it also gives you better color, flavor, and taste. If you see the picture on your on the top on the right, you see these are the chilies they dried on. One product is one sack is dried in chimney dryer, and they looks better compared to the one that been dried in usual or traditional way. And we also have some backings about the food safety. Here is some data. One university in Bangladesh, Patuakhali Science and Technology University, they did some analysis, and they found the total salmonella count and E. coli is very lower in chimney dried fish compared to the usual dried fish that's been just drying in the open air. And when they stored this dried fish, two types of drying in a for 2 months, they found that still the number of salmonella, E. coli, and vibrio is far lower in chimney dried fish compared to the traditional drying fish. And they are about to publish this paper. It's not published yet, I believe. And here, once our project is over, there's some other project who work in Bangladesh in coastal area. They came forward and kind of adapted our technologies, and they also scaled it up. So far, 3 projects. One is USDA, WFP, and Ecofish. And they built 38 chimney dryer in combined, and almost trained 650 50 beneficiaries. And like this, like all their operation is kind of in a coastal area. And here in the coastal area, if you know, like we have like a kind of crisis going on there. Lots of like Rohingya people came in there. So, and it kind of put a lot of pressure on the host community. So the aim of this project was to kind of make them, nutritionally little bit like established. And we also made a prototype higher capacity dryer, because I'll show you the challenges so you can know why we tried this. Because like there's lots of like one of the challenges we are facing, that the size and the capacity of chimney dryer. Like if you want to do it commercially, people are like complaining that it's like a far smaller than their capacity. So thinking that in mind, we tried to make a bigger chimney dryer. So here in the picture, you see the chimney dryer you're seeing is kind of like a twice or thrice the size of the usual dryer. And its total capacity almost 40 kilo. And we tried fish, like different kind of fish. So far I remember we tried 6 or 7 kind of fish, and like a drying was faster. Like, we almost dried the fish in 3 days, where the usual time was like 5 days if you just do it in an outside, like just in open air. And there's some other challenges, like it's the food habit. In Bangladesh, we are not very much, what is called like a very much known for eating dried food. Like, when it comes to fruits and vegetables, we usually go for the fresh one. And there's another challenge that's kind of, when we run a project, we are running our project in Bangladesh, like the beneficiaries are kind of too much dependent on the project support. And the problem is, like, once they're too much dependent on the project support, once the project is over, they kind of shift back to their usual practice. And there's also always lack of concern of food hygiene. Like our hygiene just go by is go like, if you see something clear, you just consider it like a good to eat. And there's a weather condition, because we have a very high temperature and high humidity. Also, we have like almost 4 to 6 months of rain, which is not a very good like condition for drying. And yeah, and this humidity and other things kind of make the dryer, sometimes you have to repair like frequently. And people are not very willing to do it, and because they find it easy just to drying it outside. So yeah, that's pretty much from my presentation. I would love to answer if you have any question. Thank you.
Thank you, Rana. I have a question. Did you have any challenges sourcing any of the material needed for the chimney dryer in Bangladesh?
No, not really. Like, you'll find the plastics, you'll find the wood logs. So I think it's not a challenge for Bangladesh to like making these kind of technologies. But you have to do the repair. Like I would say, you have to change the plastic at least every 2 months. And when you like, let's say you were drying and the rainy season hit, in that case, you cannot dry and you have to take, dismantle your dryer and other things. And once you get back after the rainy season, they are not in a very usable condition. So you have to change them, at least the plastics.
Great. Thank you for that, Rana. And maybe some more questions will come up in the chat, but we'll move on to another dryer that was more recently developed through the Horticulture Innovation Lab, and I'll play the video for the UC Davis Pallet Dryer.
UC Davis Pallet Dryer is designed to solve a problem that's often raised by the DryCard, which is that a farmer's products may not be dry enough to store safely. Particularly with grains, this raises the issue of how to dry them if they're not already dry enough. The pallet dryer is designed to replace methods that are traditionally used such as putting the grain on a road, on a concrete surface, on a roof, or on the ground. The pallet dryer uses a sheet of clear plastic, a sheet of black plastic, or in this case black weed cloth. Under that is a layer of mulch that serves as insulation. You can use straw, rice hulls, wood wool, and then underneath that, if the ground is wet, we've got a layer of tarpaulin or plastic to prevent the water from the ground, reducing the efficiency of the dryer. The plastic sheets are held taut by bungee cords attached to a wooden cleat in each corner of the clear plastic sheet. The bin that holds the product to be dried is constructed from a pallet and a sheet of plywood or MDF or other sheet goods. The floor of the bin is formed by a pallet, and the pallet is covered by a mesh of a small enough size that the product being dried won't fall through. The clear plastic under the bin is cut to allow the warm air collected by the solar collector to move up through the product being dried. This particular bin has got a hinged lid which makes it easier to put the product in and then close the lid. You can screw it in place if you want to hold it firm. And then there's a solar panel and fan, and the fan draws the warm air through the product when the sun is shining. Under typical conditions, this solar dryer can dry 250 kilograms or 500 pounds of corn in about 2 days. Much faster than drying it in the open air, where a 3-inch layer may take as much as 4 or 5 days to dry.
And now we'll hear from the actual person in that video, Dr. Michael Reed, Emeritus Professor of Plant Sciences at UC Davis, who'll be presenting on the pallet dryer. Take it away.
Thanks, Archie.
Mm-hmm.
So, as mentioned in the video, the pallet dryer is intended to deal with the problem that farmers find that their product's not dry enough to store safely, and particularly for grains and pulses, so things like peanuts and chickpeas. The chimney dryer doesn't have the capacity to dry the amount of product that a typical smallholder farmer might be producing. As has been already discussed, frequently product is just laid on the ground or on tarpaulins, and this raises the issues that Rana mentioned of contamination, possibly of predation by birds or rodents. Frequently, especially with climate change, episodic rains require that the product be either covered or taken in, and then that results in more cost in terms of handling the product and losses through that process. There are solar dryers, there are gas and electric dryers, hot air dryers that Kent mentioned, but all that we've seen are pretty complex and relatively expensive. This pillow type dryer that you see here is sold by Grain Pro, costs about $1,000, and it involves a solar collector that you can see. The grain has to be turned with a mechanism. There is a fan in there, but it's kind of cumbersome and, as I mentioned, quite expensive. So the pallet dryer is intended to provide a solution to that problem. It uses simple, inexpensive materials, discarded wooden pallets and 1 sheet of plywood, and a small solar panel and a fan. This diagram here is a cutaway or a sidewards diagram of the dryer. You can see the sheet of clear polythene that collects the heat. The black layer down the bottom absorbs the sun, and then the warm air flows underneath and up through the bin and out through the solar powered fan. The insulation under the black plastic, we found that that helped with efficiency. It's not essential, but any cheap, locally available material can be used. Straw, rice hulls, we've used fiberglass, or particularly wood wool or sawdust works quite well. In the US, the estimated cost for all the materials for this dryer is about $100. We've tested the dryer extensively and it seems to be extremely efficient. A typical experiment, one we ran recently, we used 500 pounds of maize that was at 20% moisture content, and we put it in the pallet dryer or in the open air under California summer conditions, and measured the hours it took to dry to a 0.65 water activity level. This graph here shows the temperature profiles in the dryer. The gray lines are the temperatures at the bottom of the bin. So that's how hot the air is after it's been heated by the solar collector. The blue temperatures here show the ambient temperatures, the daily ambient temperatures. And then the yellow or orange graph shows the temperature above the grain. And you can see during the first day and the second half, most of the second day, the temperature is well below the temperature that's coming into the grain at the bottom of the bin. But thereafter, it pretty much tracks the temperature that's coming up through the bin. And that is because the grain is dried and is no longer absorbing heat as it releases moisture. So looking at the data, these are typical results from the dryer. You can see that getting down to 13.5% moisture content or 0.65 water activity in the pallet dryer took about 1 day, and in the open air took about 3 days. So the dryer is much faster. It's relatively cheap to construct. It results in a product that is less susceptible to contamination and predation, and it involves less handling than trying to dry product in the open air. So we're very excited about this dryer and feel that it has a real opportunity to be used in the developing world. Oops. And I think that's my slides. Be glad to answer any questions if anybody has any.
Michael, I'm curious, can the dryer be used with fruits or vegetables? Have you done any tests with that, or primarily with grain?
Actually, we have, Archie. We initially tried to use it. Let me just see if I've got a slide of that. We tried to use it just by putting trays in the dryer on top of each other, and that didn't work very well. So then we developed a technique. Let me just share my screen again, see if I can find it. See if this shows up. No? Stop sharing that screen. I'm going to make this work. Sorry. I guess I can't do it. Yes, so what we did was we developed a dryer based on the pallet dryer, but we just laid trays alternating from one side to the other to create what we call a serpentine path of air over trays of product in the pallet bin. And we were able to dry tomatoes. I've done zucchini and figs and other products very rapidly, comparable to the chimney dryer, but actually you can put a lot more product in the pallet dryer because of course it has a much larger collector area than the chimney dryer does. So thanks for that question.
Thank you, Michael. And to catch up on time, we'll move on to the next technology, but I noticed there's some questions in the chat for you.
Okay,
And we're going to actually move on to the cold chain, and I'll be playing a video about evaporative coolers. The Zero Energy Cooling Chamber, or ZECC, was invented in the 1980s and relies on evaporative cooling. Made of bricks, sand, and a relatively simple cover, ZECCs are a low-cost cooling solution for small-scale fruit and vegetable producers and traders. The sand sandwiched between the two walls of bricks is saturated with water, in this case by water in a raised rain barrel through a drip line buried in the sand. A pitcher of water repeatedly applied to the ZECC throughout the day can also serve as a water source. The water saturates both the sand and the bricks, and using low-cost clay bricks are best due to their porosity and water retention. The water molecules absorb heated air and evaporate, lowering the temperature inside the unit as much as 10 degrees Celsius less than the outside temperature, and requiring no power source. Furthermore, the evaporative process helps maintain effective levels of humidity. The produce is then stored inside the structure, benefiting from cooler temperatures and higher relative humidity compared to the outside. This charcoal evaporative cooling unit operates on the same principle as the ZECC. However, it uses charcoal in the walls of the unit. The charcoal is saturated with water, in this case a drip line attached to an elevated rain barrel. The produce is then stored on the inside of this unit. A benefit of the charcoal evaporative cooler is that it can be built to a height and size similar to a small cool room that one can enter. This is a constraint with the ZECC, as the bricks cannot be mortared in place, as this prevents water saturation, severely limiting the height the ZECC can be safely built to. As with any evaporative cooling unit, pot and pot, the ZECC, or the charcoal evaporative cooler, they are much more efficient in dry climates, as the air has greater capacity to absorb vapor. This also means that ideal locations are dry climates with sufficient water access, which can be a challenge to find. In humid climates, produce can decay and mold rapidly in the evaporative coolers. The ZECC and the charcoal evaporative coolers are also susceptible to pest contamination, and the ZECC is not terribly ergonomic, as it has to be built low to the ground. Regardless, these units are suitable and effective for short-term storage of fruits and vegetables. They are low cost and use widely available material and can prolong the quality of stored fruits and vegetables. I would like to turn it over now to Rashmi Eka, food loss expert. Rashmi worked with the Horticulture Innovation Lab with the ZECC in Rwanda and Burkina Faso. Take it away, Rashmi.
Good afternoon, everyone. So I want to start with, just reminding a little bit about what Beth said in the beginning about food loss. So for fruits and vegetables, in developing countries, 30 to 50% of perishable product can just go bad before it reaches the consumer's home. So here I have photos of, a tomato being harvested in the field, and then the way it's transported in. These are photos from Rwanda, in these woven baskets, and then being sold in a market. So in this kind of a chain where there is no temperature management and lack of packaging and good transportation solutions, we can have very high waste. Now, produce, just like us, starts dying the moment it's harvested. So it's really important to cool it down early, as soon as it's harvested. I don't know if Archie's, you'll be, sharing these PowerPoints, but I just put a picture in here about how evaporative cooling really works. We've placed many evaporative cooling devices in Rwanda and Burkina Faso. And here I have a testimony from a president of a co-op who said that, after they built the ZECC, they are able to see a decrease in weight loss and quality loss. And they're able to spend more of their time farming and doing, field work than trying to rush to the market every day to sell as soon as possible, because every hour that the fruits and vegetables are out, they're shrinking, they're decaying. So there's always this rush to sell as soon as possible the same day. And now they don't have to do that. So now they're just selling their vegetables twice a week, and they can just store it in the ZECC in the meantime. It's another way that we've seen cooperatives use it is just, once they harvest it, they just keep it there. And then whenever the buyer comes, they're able to sell, and the produce is looking really good. It works really well for leafy greens. We did research on the ZECC with Eric Verplogen from MIT's D Lab in Rwanda, as well as in Burkina Faso. And I have links to these reports in the PowerPoint. On the top right here, these are photos of what it looks like when we had these sensors on ZECCs, and the bottom we have the same sensors on the clay potted pots. And what our research showed was that the evaporative cooling devices maintained high humidity of greater than 95%. They were also able to reduce the peak daily temperature by 7 to 15 degrees Celsius. And, it never went over 30 degrees Celsius. It also reduced the amount of fluctuation that happened throughout the day. So the temperature was held at a more constant temperature. And in Burkina Faso, we saw that the clay pot and pot design, which is this first design, that worked the best. So we did, I want to say 8 focus groups with farmers in Rwanda, and we asked them about a range of technologies, including the ZECC, and this is what they said. They said it was helpful for individual farmers. When we say individual farmers, it's really talking about the scale of the ZECC. ZECC is, it's small. We can hold about 3 or 6 crates, an average size ZECC. So it doesn't really work for very large farmers. For cooperatives, they can, put several of them in their facility. It's very useful in increasing shelf life. It keeps the quality high, again, especially for leafy greens and other very perishable produce. It's helpful when you don't have a buyer or a good price, and you can just wait for that better price or for that better buyer to come through. And again, it increases our profit, and amaranthus, which is a leafy green, can be stored in it. The main challenges were really around the volume, like how big this is. And this is similar to what Rana was saying about the solar dryer. Cooperatives are, some of these low cost technologies are kind of small in size. And so there's this challenge of trying to make it big enough for larger volumes. The ZECC, even though it's low cost, it does cost some money. Bricks are not always cheap. In Rwanda, it cost us about $150 to put together a ZECC, which doesn't cost a lot, but for some farmers that is cost prohibitive. The other thing is that you need to have the ZECC in a secure place. It's really a very makeshift kind of a structure. There's no real way to lock it. You can have a lot of theft. It does easily break down. In Burkina Faso, they have flash floods. So in a flash flood, it would just, be swept away. And because of that, there is this itch to try to make it more permanent by, putting some kind of like concrete. But if you do that, then the evaporative effect really doesn't happen. So it reduces the efficiency of it too much. So these are some of the main challenges. And then to wrap it up, I have a few resources. We have a video on how to make a ZECC. We have the research report, which we did with the sensors in Rwanda and Burkina Faso, a best practices guide, and a evaporative cooling decision-making tool, which will tell you, whether the weather conditions of a place will lend to having an effective ZECC. That's really that, the temperatures have to be high enough and the humidity has to be low enough. So under 40%, it works very well. Thanks, Archie.
Thank you, Rashmi. I have a quick question. I was curious if you think the ZECC works better with certain horticulture crops versus other ones.
We've tested a wide range, and it seems to work across the board for anything that you would like to keep in a humid environment. Yes.
And another question in the chat that came out, what was the cost that you mentioned it, $100 and something?
$150. And that was mostly the bricks and the sand. But we also encourage farmers to keep their produce in crates when it's in the ZECC, not directly in the ZECC. So there's a cost of crates as well.
That makes sense.
Yeah.
Well, thank you very much. That was really informative, and there'll probably be some more questions in the chat. And now we'll move on to a little more expensive and high-tech cooling system, the CoolBot Cold Room. And I'll play that video now.
Store It Cold Company's CoolBot device is a low-cost cold room option for storing fruits and vegetables. The CoolBot device converts a home air conditioning unit into a cooling source capable of generating temperatures suitable for the storage of fruits and vegetables. Although a home AC unit goes to approximately 62 degrees Fahrenheit or 17 degrees Celsius, suitable temperatures for a home, the CoolBot, using a heating element attached to the temperature register of the AC unit, controls the unit and drives the temperature to below this threshold in the room to whatever temperature desired by the user. A sensor inserted into the fins of the AC unit helps the CoolBot device lower the temperature at a rate that does not cause freezing on the fins of the AC unit. This demonstration video shows a unit that took this technology a step further by having the cold room be powered with lithium-ion batteries that are charged with solar panels. However, this is the only one that we know of, as most run off the grid or generators. A 48-volt split AC unit and the CoolBot device run off 4 12-volt 100-amp-hour lithium-ion batteries in the solar CoolBot Cold Room. During the day, the batteries are charged by 6 245-watt solar panels, and during the night, the lithium-ion batteries are sufficiently charged to keep the unit running. The walls are made from aluminum-sided polyethylene foam. These insulative panels are actually the major driving cost of the CoolBot Cold Room. However, using ineffective insulation when building the unit will ultimately lead to higher energy costs, either as gas for generators or electricity through the grid in non-solar CoolBot cold rooms. A turnkey cold room unit from Store It Cold costs as low as $4,200 US, making it a great small-scale option in many parts of the world. And the CoolBot device alone is available through major retailers at $350 to $400 US. Furthermore, the component that frequently breaks or needs repair is the AC unit, which can be fixed by a local AC repairman or by sourcing readily available parts. This makes the CoolBot unit extremely versatile in terms of where they can be built and maintained. For even higher cost savings, an AC unit and the CoolBot device can be installed in a non-functioning cold room, as the Horticulture Innovation Lab did in Guinea, or it can also be used as a mobile unit on the back of a truck. Specifically for fruits and vegetables, the CoolBot units do still maintain sufficient levels of humidity in the room. The Horticulture Innovation Lab has successfully built non-solar units around the world. Some challenges in developing countries are the price point, which is still relatively high, sourcing high-efficiency insulative panel walls, and inconsistent power sources provided through the grid. Some potential solutions for overcoming the high costs are for farming cooperatives to communally purchase the units and to utilize existing cold rooms, as mentioned before, or using creative low-cost installation solutions. Regardless, there is an enormous potential for the CoolBot to be used as a storage solution for small-scale producers around the world.
I'd like to now turn it over to Mamadou Cham, who's the former chief of party for the Horticulture Innovation Lab in Guinea and implemented several of these CoolBot devices in country. Cham, do you want to take it over?
Yeah. Hi, Archie. Thank you for this opportunity to speak to the group. I hope everybody's doing well and staying healthy. Just want to take a couple minutes. This is going to be like a quick presentation about what we did as a showcase in Guinea. So like many of these technologies, we saw the opportunity to, to give farmers something that they could use to store the goods before they get to market. And it was, relatively low cost, like the video is showing, and it was perfect for startup enterprises, but not somebody who is just, starting from zero. I guess somebody who's evolved a little bit more. The smallholder farmers can increase their revenues and extend the fresh food availability to the market and to the communities. And they can access a distant market, so they can actually get more money for their produce. The challenge was, excuse me, to access this the panels that are readily available in developed countries. They don't exist in Guinea. And people started taking apart refrigerated trucks that were used to ship fruits and vegetables in by sea, taking them apart and using it for construction, for low cost constructions. So some of that was available, and some of these challenges were just really downright economical. Somebody told me that, okay, well, this CoolBot thing is really cool, but how can I be sure that it's good? They don't trust the technology because it's coming from somewhere else. People don't use it. People don't know in Guinea. How can we overcome that? And somebody else came up to me saying, okay, if I myself build one CoolBot on my farm, and then the chain is not respected all the way to the market, that's not going to be, it's not going to be sufficient to just build one unit. So just some of the challenges here, and they're really valid. So what we thought on a project in Guinea, and with the help of a backstop, we decided to build a CoolBot unit from scratch on a demonstration site in Guinea. So everything was locally sourced. We use plywood and some lumber that we purchased locally from the market. We got a 9 BTU unit, AC unit that we could buy. It was really expensive. It was probably like $200 or $300 the unit. And the CoolBot that the project has imported in Guinea. So all of this stuff was readily available in Guinea that we are able to use to construct the CoolBot on our demonstration site in Kindia. So after we do this demonstration, we're trying to do like twice a month, sometimes 2 or 3 times a month, and people will come and we showcase each technology, and they were starting to get really interested in the CoolBot. And so as a result of our demonstrations, people started getting interested in it. They're like, well, I want one. Everybody wanted one. I had some CoolBot left from the project. So I told them, I can't build you a CoolBot, but if you build the structure, go find your material, go find your all this stuff that you need to build one. I could offer you a CoolBot as an encouragement. So I had 4 people actually invested their own money, spend about $800 to $1,000, maybe a little bit more, to construct the whole. Somebody just used mattress pad like we did at the demonstration site, and some people were able to get some containers taken apart so they could use parts of it to build a smaller structure, and so on. So these 4 people were able to construct the all cold rooms and get the AC units. So I came in, I installed the CoolBot for them, and they worked perfectly, and they were excited about it. So the CoolBot we constructed at the demo site were being used by our Avineers, and they're being used by some local farmers that were just coming to store the product there before they get it to the market on the next day. So I think that's it. This just goes to show that sometimes we can think that a technology is really cool technology, but then you get to the environment where it's actually not very accessible by the people that we're working with, or the beneficiaries. So how do you go to to show it to them, to make them accept it, and so they can be more so interested that they can actually be willing and able to get it themselves, rather than having the project to continue to support them. Anyway, I think that's it.
Thank you so much,
Well,
Sean.
thank you guys. So I'm open for questions. You can contact, or I know we're running out of time, but I'll be available for questions.
Great. I'm curious, do you know whether those 4 local farmers that constructed the 5 cold rooms, are they still using them now?
Yeah, I talked to one of them actually. The guy who constructed 2 of them. He had one set up at his farm and one set up on the store in Conakry, a distance of probably like 40 kilometers between his farm and Conakry, and he's still using them. He's saying that his AC unit at the store in Conakry is kind of running down. I think he used the used one. So that one is kind of not holding up very well, but the other one is still holding up very well. I don't know. I haven't been able to keep track of the rest of them.
That's great. Another question from the chat is, I believe this is correct, Rana. How often were the cold rooms being used by the beneficiaries? Were they full most of the year, or was it just?
So the one we had on our demo site, they only use them during the season, which is March and April, which are the hottest months in Guinea. So when they harvest, they will be able to keep them in there overnight before they get them to market. So if you think of Guinea, just like you were saying, Bangladesh, we have like 4 to 6 months of rain in a year. So when it's raining, they don't grow a lot of vegetables. It's just it's a dry season crop. So they only use them during the short period in the dry season. Yeah.
Well, thank you so much, Chom. That was really interesting.
Yeah.
And we're at 3:01. Great timing, everybody. I just wanted to say a big thank you to the presenters. That was really wonderful. This was recorded, so this presentation will be posted on the Horticulture Innovation Lab website. I sent the link for that website in the chat. And a lot of these technologies, almost all of them, except for the DryCard and the drying beads, are actually on display here at UC Davis at the demonstration center that we have. But I don't know if, Beth, you have any closing comments? But
yeah, I'll just echo what you said. Thank you so much to all the speakers for sharing your expertise with us. The real world experience of and familiarity with these technologies is super valuable to everyone. And so thank you so much. And thank you, Archie, for organizing the webinar. And thanks to the participants who joined us.
Take care,
Thank you.
everybody.
Thank you. Bye.